In this video, let's take a look at Newton's second law, and I want to focus your attention on the process of the second law and how it's not about memorization. Instead, it's a method of analysis that rests upon some important concepts and some skills. And there's a lot of conceptual reasoning involved when you're looking at a physical scenario and you're analyzing it with Newton's second law. And after you do that, you produce new information about the world. And so what you want to be able to do in these types of scenarios when first learning physics is not just kind of like plug through some numbers and see a certain style of problem and then repeat that same problem again and again and again. Instead, you want to be able to gain the skill of doing the whole process, which opens up this whole world of analysis for you, and you would then be able to look at a scenario that you've never seen before, or maybe something that's a little bit different than you've seen before, and you'd be able to solve it. And that's an incredible thing. So to gain that skill, let's take a look in this video about this process, and I want to help show you some good practices as you approach new problems. So let's get into that. Let's look at a numerical problem. Eventually we want to get to problems that only have variables in them. That will lead to a more general analysis, and there will be a lot more information that we can glean from the system if we keep everything in variables. But for now, we'll take a look with a simple numerical example. So we have a block. It's accelerating to the right at 8.1 meters per second squared. The surface applies a 30 Newton friction force as the block slides. Now, I've given you all the information you would need to go and figure everything out about the future of this physical system. So if you want to, you can pause the video now and try to list out all the things that you could solve for. It's a good exercise to do because when you see what I'm going to ask you to solve for, and we'll solve for everything we can here, you'll get a good sense of if you're able to look at this problem from a higher level and understand what you can even solve for here. Okay, so pause the video, and what types of things could we know about in this problem? Go ahead. All right, well, here's a quick list. We could solve for the tension in the rope, the weight of the block, the normal force exerted on the block, the net force on the block, and the horizontal and vertical components of tension. We could also do something with friction, but we'll get to that at a later time. We haven't learned enough about friction quite yet. So how do we do all this stuff? Well, we need to look at the process, all right? So let's do that next and see if you can reflect real quick. What is this process? What should I do first? Think about that and we'll take a look. All right, well, the first thing to do is identify the object under analysis. It's always the first step. So in this problem, it's pretty easy. There's really one object that we're concerned with. And so we'll draw a dotted line around the object under analysis, just the box. Next step, identify the forces on this object under analysis. And that's a simple thing, contact versus non-contact. You literally look with your eye and you see if there's anything touching the object first, and then you think about any non-contact forces. And then finally, with that information, you would try to sketch out a rough free body diagram, which is an attempt at first to indicate the direction and the approximate magnitudes relative to each other of the individual forces that you've identified. Now, this rough free body diagram just helps you kind of flesh out your thinking in the beginning. There might be parts of it that end up being wrong ultimately, but it gives you a first indication of what you're thinking to help you move forward. So pause the video. I'd like you to do these three steps here first. We've done the first together, so identify the forces and draw a rough free body diagram the best you can with the magnitudes and directions of the forces, and then you get some feedback towards the end if you were able to think about those magnitudes and directions correctly before actually solving the problem, which is a skill that will, be built up over time, and you'll be getting more and more of these kind of like rough free body diagrams correct before you go through the full analysis with Newton's second law. So pause the video and try these things. Okay, so here are the four forces that you should have identified. Number one, there's a force of the rope on the block. It's a contact force of type tension. Then we have the force of the surface on the block. It's a contact force type normal. Then we have the force of the earth on the block. And that's not this ground here. It's like the whole planet Earth. That's a non-contact force, gravitation. And then the surface also applies another force on the block. And it's a contact force, but it's a friction force. So the surface really is kind of doing two things at once, which is interesting. Now, I don't want to draw the exact free body diagram for you quite yet, but I will just say the directions of these forces. So the rope is pulling up at this 30-degree angle. The surface, the normal interaction is pushing vertically straight up. Gravity is pulling straight down, and then the friction force is pulling to the left. Now, in no way have I attempted to draw the magnitudes correctly right now. I've just really just drawn the direction, okay? Because we need to do some serious thinking about the magnitudes in just a second. All right, so let's now consolidate this information. We'll clean up the notation as well with the subscripting so we can have some more convenient variables to work with in the next part of our problem. All right, so next I like to clean up and simplify the notation here. So force of gravity, normal force, force of friction, and then a tension force. And I tend to like to use capital T for tension forces. All right, so that's a nice clean notation here. So when we get into the formulas, it won't be cumbersome. And then now literally just write down the second law in component form. Don't think about it, just write it. All right, so I'll do that right here. Add up all the forces in the horizontal direction, and that is going to be equal to the object's mass times its acceleration in the horizontal direction. And then do it again. Add up all the forces in the vertical direction and set that equal to the object's mass times any vertical acceleration. You can see how I like to line this up on the left and on the right, and then we go vertically down as we analyze the horizontal and the vertical. And sometimes you'll want to analyze one of the dimensions before the other because you maybe have more information there, but then you'll need to go back to the other dimension, like the horizontal, gather some more information there, and then maybe go back to the vertical, back and forth. There's really not one way. It just depends on what you're given in a problem, how much information you have about the system, and that's the art of kind of weaving through a physics problem. And so therefore, I hope you can see why it's critical to get this onto the page and keep it organized. So when you do need that information to push through to the next part of the problem, you have it kind of staring at you on the page. You will absolutely not be able to keep everything in your mind because there's just too much going on typically in these problems. So keep it organized and write it out on the page, and that'll set you up to successfully analyze these. Okay, so in that same light, I'm going to go to my next slide here and kind of clean everything up and get us ready to now go into what the second law is telling us to do. Now, the next part of the process is using the second law. And the way we do that after we've written it down is we use it to create equations. It's this information generating machine. So you can think of it like a little box here with, I don't know, like some gear wheels or some stupid thing like this, right? Okay, not very good at drawing this, but I'll just try to do this real quick. And essentially, you put in information, and then you create new information about the world. This is the second law machine. Okay, and so that's what we're doing here. And then after we create the equations, we can solve for unknowns, and then we can interpret and evaluate our results. And when doing this in numbers, of course, we get numerical answers, and then we can take a look at those and see if they make sense. But more importantly, when we get to things just in variables, then we can look at the equations that are generated in the final results and then use skills like proportional reasoning and extreme thinking and really understand how the system behaves when we change certain things about it. And that's a very powerful thing that we're going to build up to. Okay, we won't see that here that much because we're just working in numbers. And then we're pretty much done. The last thing you would probably do in a problem after all of that is just make sure you had a final or formal free body diagram that would outline all of the forces and their magnitudes and just make sure you're communicating that correctly. So let's do all these things and make it happen. All right, now while you work through this, I would like you to focus on solving for these two things. Number one, determine the tension in the rope. Number two, determine the normal force on the block. There's enough information here to be able to do both of those things. So I want you to pause the video and spend some really good time doing this. And you'll be analyzing the horizontal direction And then you'll also have to analyze the vertical direction. You'll be coming up with equations, writing those down, and then using them to solve for these things, right? So let's go ahead and do that. And why don't you focus first on the horizontal direction and then focus on the vertical direction. And then we'll work it out. All right. So pause the video and spend some time doing this. And I'm just going to remind you again here, this is really important. If you haven't worked this out, you're really not going to gain much from just kind of like watching me do this right now. You have to have paused this video and gone off for however long it takes and to put a very good effort into trying to solve this. Even if you don't get anywhere, that process is where the real learning is going to take place. So go ahead and please do that. Pause the video and we'll be back and we'll work it out. All right, thank you. All right, so hopefully you've kind of gone off and done some good thinking here. And here's some tips. First, concepts are key. We'll articulate those. Visualization, trying to see this scenario play out as time goes by. It's another skill that you'll be developing. A way of simple thinking, meaning that a lot of times there's so much going on, and if you can break problems up into little parts and then just think simply about those little aspects, then you can kind of piece things together. So try not to overwhelm yourself with everything going on and try to think simply. And that, again, builds up over time. And then logical thinking. There are things that have to be true based on information given in the problem. And then from those things that are true, other things must follow. And if you can follow that line of logical thinking while breaking things down into parts and trying to visualize everything, then you've got a good chance of that. So let me kind of walk you through this whole idea in the horizontal direction. Let's kind of draw it out again real quick. We've got a situation like this, and we're pulling up with some tension. All right, so first thing to realize is that we are accelerating to the right with an acceleration of positive 8.1 meters per second squared. And what follows, therefore, is that if we have this horizontal acceleration of that amount, then there has to be unbalanced forces pulling on this object. So if we have forces that are pulling to the right, and we add all those up, those are going to be a little bit bigger or a lot bigger than the forces that are pulling to the left. So we have a net amount of force pulling to the right causing this acceleration. So we're seeing a very key concept here, and we're recalling that forces cause acceleration. Specifically, a net amount of force causes acceleration. And then we're drilling down into the different directions. All right, so then what forces are causing that acceleration, right? Well, you should have identified that we have a friction force that's pointing to the left. Okay, so friction's going like this. And that kind of comes from the visualization where you're kind of watching this thing go to the right and you're realizing that it's running into the surface, kind of bumping into the little grooves of the surface, and those little bumps are pushing it, to the left. So not too hard to kind of understand that, but it's not stated to you really. It told you that there was 30 newtons of friction, but you had to reason the direction of that force, and that matters because if you get the direction wrong of friction, well, you're not going to get to the correct results here. Okay. So that's a force. Now there's only one force to the left. Next question would be, all right, well, what's pulling to the right, and how many things are pulling to the right? That's a little tricky here. And I'll say that there is one thing pulling to the right, but you have to look at this rope and break that up into components. So let's do that. And hopefully what you have done here, and I guess I'll draw this down here. If you drew out this tension force and you labeled that T, again, we don't know what it is, it's an unknown. Hopefully you realized we could break that up into components. So there's a horizontal pulling of tension. I would label that Tx. Makes sense. And then there is a vertical pull upwards of tension, and I would label that Ty. And this is 30 degrees. We've gotten that on the page, and now we're in a position to create a little mathematical formula using some trigonometry. Do that in a second. All right, so we can see here that this tension is pulling to the right, and then we have friction pulling to the left. So let's symbolically do what the second law now says to do. This is part of this process. Add up all of the forces in the horizontal direction, and that has to be equal to the mass of the object times the horizontal acceleration of the object. And we'll do that before plugging in any numbers. Just do what it says. All right, so we'll add up the force of friction plus the tension force, but not capital T. It's the tension force in the x direction, and that must equal mass times acceleration. Okay, that's a true statement. All right, what comes next? Well, notice I've not plugged in any numbers, and I haven't even worried about the signs yet, the positive and negative signs of these respective forces. In the back of my mind, I certainly know that friction's to the left, so ultimately it will be a negative number. And I know that the horizontal component of the tension is to the right, and that will be a positive amount of force. And so whatever happens here, when I add these two things together, I better get a positive number because I have a net force to the right, and I'll end up showing that here when I plug in for my numbers. One thing I actually forgot to mention a little while back is the sign convention, so just always make sure you got a sign convention. So we'll have positive to the right and negative to the left for horizontal, and then vertical, we'll do the classic. Positive is up and negative is down. All right. All right, let's keep going. Let's see what information we have. And kind of when you're new at this, it might be helpful to just look at the equation you've constructed and just go through term by term before you plug in numbers. Just ask yourself, do I have this or do I not? Force of friction, do we have it? Yes. It's negative 30 newtons. Horizontal tension, do I have that? No. So I would want to solve for that. The mass of the object, do I have that? Yes. And then the acceleration horizontally, do I have that? Yes, it was given. So let's go ahead and plug it in and see what happens. So negative 30 newtons plus my horizontal component of tension must equal 7 kilograms times 8.1, positive 8.1 meters per second squared. Great. Now we'll solve for this. And what I'd like you to do now is pause the video and see if you can figure out not what the, well, you will figure out what the tension is horizontally. It's obvious now, I hope, how to do that. You'll figure out the horizontal tension. But remember, the question was asking about the entire tension in the rope. What is the force of that rope? What is the tension in that whole rope? Pause the video and see if you can now figure out the answer to that question based on our analysis of only the horizontal direction. All right, take a minute and try it. All right, well, hopefully you know from just basic trig that the horizontal component of a right triangle like this is just the hypotenuse times the cosine of the angle. We know the angle is 30 degrees. And we can solve. So what I would do is I just solve for the tension, which is the hypotenuse of that triangle, and we would get the horizontal tension divided by the cosine of the angle. So we plug that in, 86.7 newtons, divided by cosine of 30 degrees, which is 0.866. And when you solve it out, you get about 100 newtons. I think it's like 100.1. So I'll just, I guess I'll leave it like that, but meant to get it exactly at 100, but oh well. All right, so we got about 100 newtons of tension in this rope. And notice how we didn't really, or we weren't really told how to get to that in the very end. We had to weave our way through using the process as that foundation to do this. And at this moment, right here, when we figured this out, hopefully like alarm bells were going off in your mind, and you were thinking about, okay, now I have this piece of information, this what I'll call new info, right? What can I do with that? It's like I have a new tool in my toolbox, and how can that knock some other dominoes down, if you will, to further get through the problem? That's the thing you have to kind of get used to with these types of problems. It is absolutely not a memorization of a step-by-step procedure that you can just memorize and then redo every single time, right? It's this other thing, this process that kind of unfolds differently with each nuance of each problem. And sometimes it can unfold for the same problem in different ways because there's multiple ways to move through the problem. That's one of the really cool things about physics. But it is a little different, I think, when you learn this for the first time, because a lot of times in other situations you might have just been taught to kind of memorize things and go, procedurally, step by step, always through things. Okay, so we're learning a new skill. Let's do the same thing, and I'd like you to do this vertically or check your work vertically now that you've seen the horizontal direction. And what can we know from the vertical direction? All right, pause the video and try that. Go ahead. All right, let's focus on the construction of our formula here on the vertical side of things. And we see that we've got three vertical forces. Gravity's pulling straight down. We've got that normal force from the surface pushing straight up. But then we also have this tension pull. There's a component of tension that is vertically straight up. Now, I've written the formula out still with this acceleration term in here. I always like to do that until I have thought clearly if I know that the acceleration is zero or non-zero. So there's some simple thinking here. What is the object doing vertically? How is it moving vertically? Is it moving vertically? Well, no, it's at rest vertically. It's sliding horizontally, speeding up horizontally, but there's absolutely no motion in the vertical direction. We know those two motions are independent, and so there's no acceleration vertically, and we can cancel that out. So I like to kind of formally do that. Boom, zero. All right, now we just got to get the signs right. And hopefully you can realize the little tension's pulling up, and that's going to be positive. Gravity's pulling down, that's going to be negative. And then the normal force, that surface is pushing up. So we plug it all in, and then we could solve for whatever we want to solve for. Now let's think, do we know anything first? Well, we certainly know the force of gravity. Let's plug that in. It's going to be negative 70 newtons. Okay, remember the force of gravity is mg, the magnitude of it, and then we direct it based on our sign convention. So we'll plug that in here. Negative 70 newtons, 7 kilograms times 10 newtons per kilogram. Let's approximate there. And then the tension vertically, we'll get to that in a second. We do not know the normal force. We want to solve for that. Can we find the tension vertically? Certainly. And you can even do that before you find the total tension in the rope. If you know the angle and you know the horizontal component, you can use the tangent function. So I've written that out over here. Tangent of theta is the vertical over the horizontal, opposite over adjacent. And in doing so, we work it out, and we get that I'll let you work that out, but the vertical tension is about 50 newtons, or 50.05 if you're just following my exact rounding. All right, cool. So we'll plug that in over here, 50.05 newtons. And let me sorry, it's getting a little cluttered here. All right, 50.05 newtons minus 70 newtons plus the normal force must sum to zero. We check it, make sure all the signs are right, everything makes physical sense. Tension should be positive because it's pulling up in the vertical direction. Normal force we're solving for, so we don't plug in a sign for that. And then gravity, of course, is down, and it's 70 newtons, and we did that correctly. All right, so we solve for the normal force, and we're good to go. So we get 70 newtons minus 50.05, and you get about 20 newtons or so, or 19.95 newtons. Yeah, I think I got that right. Cool, put a box around that. Now, it's important, if you obtained an answer for your normal force through the math that was negative about 20 newtons, well, then you've done something wrong. And the only way you would know that you've done something wrong is if you were to really think about the concepts here. If you kind of imagine that block hovering above the ground and then slowly being lowered onto the surface, I should say, the surface is going to push up, right? The surface is not going to pull down on the block. The only way the surface would be able to like pull down on the block is if maybe there was another type of interaction, like a magnetic interaction or something, like the bottom of both of the objects were magnetic and they were like pulling on each other like magnets do or something. That's not happening here, okay? That should be pretty simple for you to understand, but that's a nice check for understanding and check to evaluate your result to make sure you've done something correct is getting all these signs right. Awesome. All right, so now we've pretty much done everything. The last thing to do would be to draw a free body diagram. So go ahead and do that, but make sure you get the magnitude and direction of all the force vectors correct. And remember, how many forces were there here when we identified them? Go all the way back to our object under analysis, contact and non-contact. How many forces were there? Think about that. I'll remind you here. There were 4 forces. So therefore, you should only have on your free body diagram 4 force vectors. Go ahead and see if you can get it right, and then we'll take a look. All right, so I've listed the forces here, the 4 forces, and let's draw a free body diagram. I typically like to have the gravity force drawn first, and that kind of sets up my scale. So the length of this line on my piece of paper, about that long right there, represents 70 newtons. So if I need to now draw the tension force as 100 newtons, well, it needs to be larger than this line. If I draw the friction force of 30 newtons, that is going to be shorter than that line. So let's make sure we get that done correctly. All right, so the tension force is at a 30-degree angle above the positive x direction, and it's 100 newtons, so it's longer than that 70 newton force. So maybe something like about that. I'm kind of eyeballing it, which is fine, but you want to, in general, get the right idea. Then the normal force is only 20 newtons pulling up. So it's going to be maybe something like this. The normal force. Let me actually, that's fine. And then the friction force is going to be 30 newtons, so a little bit longer than that 20 newton force of friction. 30 newtons, like that. Notice I don't like to put the signs on the forces when I write my free body diagrams. A lot of times I will just put the magnitudes, and sometimes I won't even put any numbers at all. Okay, now there's a great moment here where we can take a step back and really look at what this free body diagram is communicating and make sure that it makes sense conceptually with what we've discovered in the horizontal direction and in the vertical direction. So just pause for a second, think about this. What's happening horizontally? Do we have a case of balanced forces? Do we have a case of unbalanced forces horizontally? Pause for a second, think about that. All right, and I hope you clearly identified that we have unbalanced forces horizontally. I'll even write that here. Horizontally, we've got unbalanced forces, and that leads to acceleration, which we knew from the outset of the problem, and that is clearly shown here in the free body diagram. If you visualize the components of that tension force, and this is something I do not want you to do right here that I'm about to do. I don't want you to draw on the free body diagram these components. You can certainly make another diagram if this helps you, and it probably will as you work through problems. But on your kind of final formal free body diagram, you do not want to draw components. We just want to draw the individual force vectors on free body diagrams, okay? But in doing the components here, you can see that there's a lot more pull to the right from that tension, that horizontal tension, than there is friction to the left. So that's a nice check to show that we've done things correctly horizontally. Likewise, look at the vertical and make it make sense here. So vertically, we have balanced forces. Why? Well, because the object is at rest vertically. It's not moving, and therefore the forces vertically must be balanced. Now that one's a little more subtle to see, but a quick look would show you, if you could kind of keep it in your mind here, if you added this line that thing that's 70 newtons to this line, which is I think 50 newtons, to then this line, kind of in your mind, kind of stack them up, and you can see that they essentially balance out. And if you go back and you look at your first free body diagram, your rough free body diagram, I want you to look at that and notice, what did you draw for the normal force? How large was that initial vector you kind of guessed probably if you wrote it down? You might have drawn it kind of close to the same size as gravity, which is a tendency we often have until we've analyzed the whole situation. Right? So this is a good check of understanding and how you can go back at the end and modify your original thinking. Sometimes that happens. And as you gain more experience with the problems, you get kind of better at figuring out what you should see, towards the end. Awesome. All right, well, I think with that, I want to wrap up this numerical style video where we've really gone through in great detail and taken a look at everything. Hopefully that helped you out, get the process down, and we'll be looking at some things in variables and seeing how to analyze those situations kind of at a higher level. Take care, and we'll see you next time.